Welcome back. So I hope you are following well inverse kinematics that I did in my last class. I covered 2 degree of freedom and 3 degree of freedom robots. When I showed you how a 2 degree of freedom can be a subset of higher degree of freedom robots as well. We saw 2 degree of freedom solution, multiple solutions also, even 3 degree of freedom multiple solution, which is nothing but an extension of 2 degree of freedom plus 1 degree of freedom system. Okay, so moving ahead further, so today we'll be doing spatial robots. Earlier we did 2 degree of freedom and 3 degree of freedom planar robots. So today we'll be doing a robot that can achieve position in 3-dimensional workspace. Along with that, we'll also be doing one standard industrial robot, that is SCARA robot today. And in between, we'll also do a 3 degree of freedom cylindrical robot. Okay, so these all robots are few of the selected robots which are very, very important, because at least for 2 degree of freedom robot, which is, can be a subset of higher degree of freedom robot. So solution gets very, very easy then. And special 3R robots, that is the first 3 link of standard industrial robots are mostly special 3-DoF robot. Okay, so moving ahead further, so we'll start with 3R spatial manipulator first. So this is a spatial manipulator. To make you understand better, let me just switch on some virtual environment that I have out of Robo Analyzer software, which is very popular software that was developed out at IIT Delhi by Professor S.K. Saha and team. Okay, so let me just use it to make you understand it better. Okay, 3R spatial robot, basically it looks like this. It has 3 joints. First joint, as you can see, it is vertically like this, where first link is moving along vertical axis, that is Z0 axis, which is shown here vertically. Okay, this one. And the second axis, which is parallel to the ground, it goes like this, which is shown here. And the third one is like this. I have taken 2 links, both are of equal length. So if you look from the top, it will look something like this. So this is how it is. Got it? And if you look from the side, so it can go something like this. Got it? You can see how it moves. You see it goes like this. Okay, it is exactly like a 2 degree of freedom robot. So this can move like this. Can come back to its original position like this. Got it? This time if I look from the top, you hardly see there is any motion at all. Okay. The 2 link is coming exactly in the plane. You got the structure of this now. So if I take it back, it goes like this. Okay. Now without moving or making the second link and third link exactly at the end location which was there, now let me move the first joint. You see how it moves? So I am now moving the first joint to 45 degrees. Okay, so it goes from 0 to 45 degrees. Got it? So it is a complete plane on which 2 degree of freedom robot lies. You see that plane is moving. Okay, that plane is rotating. Okay, that plane carries the 2 links, first link and the second link, which was a subset, 2R subset. So it is effectively 2 and 3 link, second and the third link over here. So if you look again in a view which is like this, so you see how it moves. The plane completely which carries the 2R subset rotates about a vertical axis. That is the first degree of freedom. Along with that, it rotates. Okay, the first joint makes the whole plane rotate about the vertical axis. Got it? So this is how it is. So let me just come back to the isometric view, which shows everything together. So yes, now I'll move the system, whole of the system from the first 2 links. So this is how it is. So you see it moves the first 2 links. the first link moves from 0 to 45 degree, whereas the second and the third link goes to 0 to 30 degree for each of them. Okay. So this time when you look from the top, it is something like this. Plane is rotating, and on the plane, other two movements are there. That is for the second and the third link. Got it? So hope you have understood well how this system it is. So I'll just switch off the virtual thing and come back to this kinematic picture. Okay. So forward kinematics, you can do it straight away using projections also, or using DH parameters. Both are equally good. So you see X. Where is your X? So this is your X. This is your X. And Y is perpendicular to X and Z. So you have Y here, and this is your Z, X, Y and Z axes. So you see this contained the 2R subset. 2R subset. So where is it? This is link 2 and this is link 3. That is completely contained in a plane, and the plane rotates about this vertical axis. This Z axis, the whole of this rotates. Got it? So that is theta 1, which is making it move. And this is your plane. So this is your plane. So now let us analyze what could be the components of 2R subset along different axes. Okay. So now what is X? You just can obtain it directly from here. So it says A2 cos theta 2. Where is that? This is your A2. A2 cosine theta 2 is this, and A3 cosine theta 2 plus theta t. So this is theta 2 plus theta 3. So cosine of that is this, and same is this. So total distance. So this is your Ex dash. Ex dash is here, and cosine of that. So this also is Ex dash. So cosine of that with theta 1 is actually your X. So this is your X. Got it? So this is your X. Now let us see how Y can be done. So Y is what? It is again Y, you see, it is A2 cosine theta 2. So you see A2 cosine theta 2. This again A3 cosine theta 2 plus theta 3. This is theta 2 plus theta 3, this one. And finally this one. So this is it. So this is your Ex dash sine theta 1. So if this is Ex dash, this is theta 1. So this becomes your sine theta 1. So effectively it is Y. So here is your Y. Now let us look how is Z taken. So Z is simply D1. So this is your D1. This distance is always there. So it brings it till here. Now how much is the remaining? So A2 sine theta 2. So this is A2. This is theta 2. A2 sine theta 2. Then A3 sine theta 2 plus theta 3. So this is theta 2 plus theta 3. This is your A3. So this is the remaining distance. So D1 plus this plus this. So this is your Z. Got it? So this 3 is quite okay. You can directly obtain by projection. Using DS parameters also you will come to this. Okay. So now let us do inverse kinematics. So this, using this, I need to solve for theta 1, theta 2 and theta 3. What is given is X, Y and Z. So using the first two equations, if you just divide them, so Y by X, this by this quickly gives you tan theta 1. So theta 1 can be directly obtained using tan inverse of Y by X. You can see from here also, if this is theta 1, so if it is Y by X, so it is directly tan inverse of Y by X should be your theta 1. So you have obtained theta 1. Now you know theta 1 straight away. So once theta 1 is obtained, you can obtain Ex dash. So what is my Ex dash? So Ex dash is simply x by cosine theta 1. This is your Ex dash, which is marked in this also. So this is your Ex dash. So this is it, Ex dash. Okay. Again, Ez dash. So that is Ez dash. As I am marking, just keep following. So this is your Ez dash. So this is your Z dash. Got it? So that is equal to Z minus D1. Both are known. Z is known. D1 is the distance from here to here. O to O dash. So this is known. X is known. Theta 1 is known from here. So Ex dash and Ez dash is known. So now you just look at carefully. These are the two equations in which two unknowns are there, theta 2 and theta 3. Got it? And you already know Ex dash and Ez dash. Ex dash and Ez dash. So can you recall your 2 degree of freedom system solution? So effectively this was your x, this was your x, let us say this is your x prime. So that is a new x-axis, and this is your z prime, that is also equal to z because both are aligned together. So this is your 2R subset. This is your 2R subset. So now what we know is Ex dash and Ez dash, two are known, this and this are known. So you can quickly find out theta 2 and theta 3 using your 2R subset solution. So you have already solved this kind of equation earlier in 2R system. So you can quickly make it like this. So this will give you theta 2 and theta 3. You just have to replace x with Ex dash, y with, it was planar system. So we took this as x, this as y. This was your system. Okay. This was A1, this was A2, theta 1 and theta 2. So I am just replacing theta 1 by theta 2, theta 2 by theta 3. So that is it. Theta 2 and theta 3 is obtained. So instead of A1 and A2, it is A2 and A3. Got it? It is A2 and A3. Got it? So exactly this you can obtain. And instead of x, you have Ex dash. Instead of y, you have Ez dash. Got it? So this quickly you can obtain theta 2 and theta 3. So now you have obtained theta 1 which was here and theta 2 and theta 3. Got it? So all the angles are obtained. What was known was x, y and z. So that was input to the system. What was known was D1, A2 and A3. So all the kinematic parameters D1, A2 and A3 were known. Okay, so all the parameters were known. So now if I tell you it has 4 solutions, how? You can quickly see this. You can quickly see this. So first solution, the one which is here visible, shows an elbow down solution for 2R subsystem. So this is your elbow down. So another one to reach to the same place could be something like this. Okay. So this becomes your new theta 2 and this is your new theta 3. So you know by earlier method, so at least these two are easily visible. Okay. So what are the other one? Now you can just see from here theta 1. So theta 1 is either both y and x positive, both y and x positive, or both negative, still you will get theta 1. So what does it effectively signify? If you look from the top, so this was your 4 quadrants. Here is your robot when it is x and y both positive. Okay. So this was the end effector position that gave you theta 1. So end effector position can also be obtained similar theta 1. You will see when you have the robot which is facing something like this. So this also will give you same tangent solution. So x is negative, y is negative, you will obtain same theta 1. That means your robot is now completely rotated by 180 degree and you are coming back. Okay, you are coming back and you are obtaining going to the same xy position. Even with xy both positive, theta 1 can be theta 1 plus 180 degree. That is till here you can reach. Okay, so this is where you are now, and now you are gone back. So this is like you can do it something like this. Okay, you are holding like this, elbow down. You can rotate 180 degree opposite and come back like this. Okay, and you can come back to the same location. So that is what. So if I can show you this robot, so it can go here this way, or you can rotate 80 degree, and this robot now can obtain similar solution going like this. Got it? So that is how it can obtain. So theta 1 is theta 1 plus 180 degree, and again you have elbow up and elbow down solution. So 2 for the front solution, 2 from behind it can do elbow and elbow down. But not all of them are achievable using any standard industrial robot, because you have joint limits, you have structure of the robot is not allowing you to do so. So that is quite possible. But mathematically it has 4 solutions. Got it? Okay. Now let us move to our old friend. Okay, so this is a 3 degree of freedom cylindrical positioning robot. It was revolute, prismatic and prismatics. First was theta 1. Next variable was D2. Next variable was D3. So altogether you see forward kinematics, we got this, can be written as, you just take this portion out that says this is X, this is Y, this is Z. Got it? So exactly that is here. Okay. Now what is given is, for an inverse kinematics problem, X, Y and Z are known. You have to find what is the joint variable. What are the joint variables? So joint variable was theta 1. This one was revolute, so this is unknown. Next joint variable is D2, because this was prismatic joint, this was revolute joint. For next prismatic joint, you have D3, which is to be found out. So all these are unknowns. So these are knowns. So you just have to solve it. So let us see how to do it. So inverse kinematic solution here could be theta 1 is simply, if you see it carefully, it is minus x by y. So just look this carefully, you just have to divide them. So if you divide this by this, you will get minus of tan theta is equal to x by y. So tan inverse x by y minus x by y will give you theta 1. So this is your joint angle theta 1, which can be obtained by just having x and y. It doesn't require z at all. Okay, now how z can be done, utilize. So you just have to use this equation now. So d2 is z minus d1. So what is that? You know, d1 is a constant. This is the offset from here to here. Got it? So that was the offset. So d1 was known. Z is, because it is an inverse kinematics problem, Z is given. So both are known. So you can quickly obtain D2. Got it? So D2 is obtained. Now D3 is just square and add, take the root. So you can quickly obtain D3. So D3 is like this. Okay. Now let us analyze its multiple solution on whiteboard. So you see, you also have similar solution that we obtained earlier. Let me draw a whole of this system looking from the top. Okay, how it should be. So this is your x0. This is your y0. and your link is somewhere over here. If it is positive theta 1, it goes like this, and this is your distance d3 that makes an angle theta 1 from the vertical. So this is your d3. Got it? So you are here with coordinate x and y. Got it? So how many ways I can reach to xy? So theta 1, from here, you know, it can be either minus x plus y or plus x minus y. Both are equally good, will take you to same theta 1 angle. So physically, what does it mean? What is this? This is minus x plus y. X is negative, y is positive. So you can also be in this quadrant. So here you have plus x and minus y. Plus x and minus y. You will again get same angle. So this also is theta 1. This is an alternative solution for theta 1. But this is taking you here. So in order to go to the same place, instead of coming d3 as positive, like this should take you d3 as negative. Got it? So this time, instead of coming out this way, you have to go back to this direction. Got it? So d3 is negative in that case. Got it? So your robot has turned not just till here, it has gone till here. Got it? So this time, instead of moving forward, you have to go backward and achieve the same xy. So this is how you see you have how many solutions? 2 solutions which are quickly visible. Here also you can see d3 is square root of x square plus y square. It says plus or minus. Is it not? So the plus 1 is considered when this is the case, exactly the one which is here. When you have negative x, positive y. Minus is considered when you have negative of y and positive of x. Got it? So these are the 2 solutions. So you have to consider these while you will be programming for inverse kinematics of cylindrical positioning robot. Got it? So this is it. Okay. Now let us come to one very important industrial robot that is known as SCARA robot. It is a 4 degree of freedom robot. You have already seen that. Okay. So this was the forward kinematic solution for that we obtained earlier. There is some addition here. This distance we took it as 0 over there. So you don't see any d2 over here. Otherwise, you will also see this. You can quickly arrive it like this. So if this is your z, okay, so that was your z direction. So what do you see? It is d1 plus d2 minus d3 minus d4. Is it not? So minus d3. So in addition to d1 minus d3 minus d4, z will be d1 minus d3 minus d4 plus d2. Got it? Others will be the same. So the end effector pose is given by this, that is xyz position of the end effector, which is here, and its orientation also. And total orientation, you know, it is sum of all the angles that your robot has rotated. Okay, your end effector has rotated along the vertical axis only, because this is the robot which doesn't have any roll and pitch angle. It can only rotate about vertical axis. So it makes things quite simple. So if this is your theta 1, this is your theta 2, right? And you also have theta 4. This was your prismatic. So the 3 was varying. So sum of all these angles is actually the total angle psi which is obtained. Got it? So unknown variables are theta 1, theta 2, d3 and theta 4. d3 is this distance. This is a prismatic joint, so it can travel up and down. So that is what. So all these are unknown. These are known. Forward kinematic equation. From here, you can directly get till here. You just see this change. Rest everything is same as we have obtained earlier. We have to use it. Okay, so your 2R friend is again here. So you see, this is your first link, this is your second link, is it not? So this is A1, which can rotate about vertical axis by an angle theta 1. This is A2, which can rotate about vertical angle, that is theta 2. Very nice. So till this point and this point, both lies one over the other. Okay. So whatever is xy for this end effector, same will be the xy for this point, is it not? So if you know xy, which you know already, so you can quickly calculate theta 1 and theta 2. So that is what we'll be using to solve SCARA as well. So I'll look it from the top. It is a 2R subsystem which is out of SCARA as seen from the top. So you see, it looks like this. So whatever is my xy, that directly can be written as position for P2. This is your A1, this is your A2, this is your theta 1. Again, you have a relative angle theta 2. Okay, xy is given. You can quickly find out theta 1 and theta 2. So this is there. So theta 1 and theta 2 can be found out from our earlier 2R solution that we did. Okay, so I have just copied it from there. So this is it. This, you know, has got two solutions. Okay, it can be like this, it can be like this. This is your theta 1 or this is your theta 1. So again, this is your theta 2 or this can be your theta 2. Got it? So these were the two solutions. So we'll come back to this multiple solutions. But for now, you know, you have already obtained theta 1 and theta 2. So D3. What is D3? D3 was also unknown. So you go back to your SCARA robot and just check what was D3. So this is what you want to find out. What all things which are known is D1, vertical distance, D2. Those are the structure of the link 1 and link 2. Link 1 and link 2 structure. Part of that. Okay. And D3 is variable. D4 is again the offset from this to this. So that is again a constant. So D1, D2, D4 are constants, whereas D3 is variable. Z is something which is known. Z is known. Got it? So let me come back to this. Okay. Z is known. D1, D2, D4, you know it. So yes, D3 can be evaluated directly. So there is just one unknown in the vertical direction. So straight away you can obtain that. So three of them you have obtained, the final one. So now you already know theta 1, you already know theta 2. Got it? End effector orientation was given psi angle. That is the total rotation of the end effector is also known. So this is known. So you can quickly obtain theta 4. So that is the vertical angle of rotation for your which link? This link. This angle is theta 4. So you have calculated theta 1, you have calculated theta 2, total angle psi is given. So from here, so that is what is here. Got it? So yes, solving these systems are very, very trivial now. Now that you know how to use your 2R subset everywhere, even 3R subset, you can use it. The one which we did today is a 3R spatial system. That is a subset which is there in most of the industrial robot. First 3 links will be arranged like that. Okay. So yes, that's all for today. For the next lecture, we'll be doing inverse kinematics of 6 degrees of freedom industrial robot. Okay. So that's all. Thanks for today. Bye-bye.